In this lesson we'll look at guidelines related to chord features, wall thicknesses, and thickness change and junctions. So let me see, as a starting point we are going to put these guidelines. So this is simple guideline. I will make from simple to more complex. So whenever there is a long thin section, and it's a little towards the top of the casting, there is going to be, the metal is going to be cool, and then you might have a cold shut problem. And the immediate guideline is, can you increase the wall thickness? As a foundry man, it looks too simple to you, saying, oh, what is this? But remember, designer doesn't understand, appreciate that. Imagine the moment you put a thin section, a warning bell comes. Oh, no, you can't do that. You have to increase the wall thickness there, or reduce the length of the section. Either increase thickness or reduce the length of that flange. So what we have is here a thick section, again common thing to see in foundries. But look at the solution here, and little more tricky. What the designer has to do is to make the wall thickness little less drastic. And you can do it either by redesigning the section, or sometimes if nothing works out, you can put a hole in the section. In this case you can put a square hole or a round hole, whatever. The hole is not needed for functionality, but only for manufacturability. Plastics and die castings, fortunately, they do these things. Somehow it doesn't, you don't see that in sand castings. People somehow think that sand castings are far more easy to make, or there's much more freedom of choice of geometry, which is true, but then there's a price always to that complexity. This we have seen in a sense as a repetition of that. Configuration of thick sections. If all thick sections are at one end, excellent, I can feed it by putting a feeder next to that. If the two thick sections are at two ends, again not a big problem, it's a minor problem. I need to only put two feeders, or one big feeder and one maybe one chill or fin, things like that. But if the thickness is in the middle, and we did see one example yesterday, so it is designed to get a shrinkage porosity at the junction. So it's designed not for quality but designed for a problem there. It's very difficult to solve that. Unless you change the part design there, that problem cannot be solved. You got to increase, put a wall thickness increase, so you can put a feeder, and feeder can feed through the thick section to the central hotspot. And so these are all junctions we have already seen. Here I am putting the picture back into saying, if it's a star junction, and remember in casting star is always bad. Okay, if you can convert star junction to X junction, great. It's a one improvement at least. Or from X, if you can make it plus, one more improvement, because that, what is different between plus and X? X has a thinner angle, and you say, what is the problem with thinner angle? Other side is thicker angle. No, sorry, the thinner angle doesn't cancel the bigger angle. The thinner angle creates a problem which cannot be solved by the bigger angle. So you have to put all the angles to 90 degrees only. Similarly, Y to T or V to L, you are going from more bigger problem to a smaller problem as you move towards that. And you also saw other guidelines, and if you remember that, what is the effect of wall thickness and length and fillet radius and other research which was done actually by Dr. Durgesh as part of his PhD. Those guidelines are available to you now. This also comes from Dr. Durgesh. What he did was to actually take a box corner junction with all complications. I mean, you not only have the 3D junctions, but also you have wall thickness difference there. And if you see the left picture, casting picture, and if you cut the corner off, you see a clear defect. Okay, so you deliberately designed the casting to produce a defect, which happens once in a while in foundries. Now, among various solutions for solving this problem, one easy solution is just put a chamfer on the corner. Okay, just put a chamfer on the corner. By putting a chamfer, the problem goes away. No other change. Okay, of course, designer has to accept that. Please remember that. And few more examples of change. Okay, if you see you can quickly mentally visually look at the changes. First pair, the hole diameter is increased. Second pair, also hole diameter is increased, also because thin hole and thick section is bad. Third example, on the left side bottom, you are making a more complicated hole into a simplified hole. That reduces the core cost. And the fourth one, too many core holes, reduce the number of core holes, maybe drill them later. Simple guidelines. Some more. If you see the first pair there, what is the difference? First pair. Anyone can actually figure out? The designers has put the draft. Oh, so nice. So there is no weight difference in my design part and manufacture part, because I am not adding any additional draft. Okay. Second one, you can see moving the mid to the rib to the middle, undercut is reduced, tool complexity or number of tool elements reduces. Third one, again you are simplifying the part shape, complexity reduces. The fourth one, an overhang portion is removed, it could make your either casting simplified or even machining simplified if you are to machine the pocket. Okay. Now let's take a look at a little more complicated problem. Okay. If you see the left side, there are two, you can say either self core or a cored core. You have one core from the left side and one core from the right side. Okay. Both of them are both of them are cantilever cores or blind holes. The region between the two cores can become very hot because there is no print, so there is no air and gas escape. You remember, prints allow your air and heat to escape, gases and heat to escape. There is no path for these to escape in the middle. So middle area you have both gases and heat accumulating. So you might get in that case a combination of shrinkage and blowhole. And also because it's a simply supported core, because buoyancy, depending on where the buoyancy net force is acting, core can go either usually up if it's ferrous metals, and you don't get a concentric hole. You get a thinner wall on the top and thicker wall of the core on the bottom side. And machining, either you have to increase allowance or even then it may be rejected. So how do you solve that? We can't solve it as a foundryman because we don't have design rights. But if a designer appreciates these problems, and if we can combine both into a single hole, and later on if he wants to plug the hole, okay, you can always bolt a addition section in place. Okay. By doing that, you have solved all the problems in one shot. Much better support on both the sides, single core cost also comes down, escape of gases and heat is no problem, and it is much more rigid, it won't move in the mold. Now we will now show you a deliberate attempt at creating a problem and how to solve the problem by DFM. This is again a laboratory experiment. Later on I will show you industrial examples of this. Can you see the original part and revised part? What are the differences in that? Core diameter has been increased. By increased core diameter, again thickness is made more uniform. Okay. And what we did, just to prove our point, we made both the castings, both the two different designs in the same mold with a same common gating system. So conditions of metal and pouring and everything are exactly same. You can't say we have cheated. Okay. By doing that, if you see, and it's made in steel here, the casting which was, and you can clearly see the thickness, the bottom now becomes the top here, right, and the bottom two pictures here. So if you see the one with the thicker section, you see a clear shrinkage cavity. On the other one, which is a combination of thinner wall as well as larger core diameter, there is no defect there. So just to prove the point that changes in design can lead to better manufacturability here, better quality here. So this is quality by design. This is quality by design, not quality by manufacturing. Okay, so to encapsulate this, what we talked about is that these guidelines, which I showed a very small example of that, and you get many more in handbooks, and also different foundries have captured the guidelines in their own way, or designers also from their past experience. All these encapsulate the experience out of making mistakes of poor designs and quality problems because of that. So they only tell you what is wrong and how to improve that, what is right. Okay. These are good for a quick check, that is okay part. Okay. And we have looked at quickly some of the major guidelines for wall thicknesses and cores and junctions and so on. Okay. The issue and the problem is, one is you do not know the quantum of change. So in the previous example we showed you that okay, by reducing wall thickness and core diameter, problem went away. But what is the limiting of that? How much I need to reduce for the problem to go away? That quantum is not clear from just looking at a picture. Of course you can always use simulation for figuring it out. But without simulation, can I do that? Answer is not very easy. The other problem is that guidelines may conflict. One guideline may say increase fillet radius, I want the metal to flow properly. Another guideline say no, reduce fillet radius because I am increasing the mass concentration and heat concentration and creating a hot spot. Should I increase fillet radius? Should I reduce fillet radius? Direct conflict. So in that case you need to be able to measure the total impact of the design change on the entire manufacturability. Total quality, my rejection is going to go up or come down, my cost is going to go up or come down by what percentage. If I can quantify the numbers finally, I can take a holistic decision, again an optimal decision. So in the next lesson we will see how to do that, how to put a number to these guidelines.